Welcome my dear students. Welcome to Kcyc channel. We are going to continue from where we have stopped last time. Gravitation. Up till now we have completed till Kepler's law. Now we are going to move further with the next part of the chapter, that is mainly with respect to gravitation, different aspects of gravitations with respect to Earth definitely, which we are going to see in this chapter. First and foremost, variation of g due to surface of Earth. That means g is acceleration due to gravity. As you know, it is not universal gravitational constant. Universal gravitational constant is capital G. I am talking about the small g, which is acceleration due to gravity. Here, variation of g due to shape of the Earth is very much significant when we say. As you know, you must have heard our Earth is not a perfect sphere. Due to the rotation part, it is bulged towards equator. Look at the figure, all of you, carefully. It is bulged towards the equator and it's much more flattened towards the pole. As I already told you in the previous class, all the gravitational pull is towards the center of the Earth. So you have to understand, when the Earth bulges out in equator, the distance, that is the distance from center to equator, that is the RE, which is shown in the figure, will be greater because the Earth is bulging towards the equator outside. Okay, but it is much more flattened in the pole. That is, when distance from the center of Earth to the pole will be much more less. That is why radius RE with respect to equator is greater than radius RP with respect to the pole. The shape of the Earth is bulges of the equator. Okay, as you know, I already told you about this. So G will be equal to Gm by R square. This is a general equation which we have learnt in textbook. It is in it's a equation number 5. I think it is in page number, just a minute. Yeah, got it. Yeah, it is in your textbook. It is there. Yeah, it's in page number 8. Page number 8, you will get the fifth equation as G is equal to Gm by R square. Okay, R square is, as you know, universal gravitation equation. In that you will get that R, that is the square of distance between the two bodies. So here we have to understand, this is the equation for it. So acceleration due to gravity with respect to equator will be Gm by RE square, the radius is taken. So ultimately here we have taken the same equation with respect to pole. Look at the pole, it's over here. So if you look at the equation, both are very much similar, but the radius is comparatively less. So acceleration due to gravity is more at the pole than the equator. Why? You know, because of this condition, because the radius is higher. That's why, in simple term, you will feel more weight when you are at the pole. You will feel less weight when you are near to the equator, because the gravitational pull is much more higher in poles with respect to equator. Next part, we are going to discuss the variation of g with respect to height. Okay, as you know, when the height is increased, like if you consider this figure, this is Earth and this is the radius of Earth and this is height. So if we always consider from the center of a mass. So here we got Earth center. So exactly this small d will be equal to the radius of Earth plus the height at which the object is there. Like for example, if here is the object, the total distance between the object will be from here to here. So you have to understand about this variation of g with respect to altitude. So just imagine there is a body at height h. the total acceleration due to gravity with respect to the previous equation, that is, I already told you, page number 8, fifth equation, it will be equal to g with respect to the height, g to the base h, gm by r plus h, the whole square. R plus h is nothing but the distance from the center to the body, distance from the center of the earth to the body. So acceleration due to gravity decreases with the height from the surface of the earth. That means as you go up, you won't feel acceleration due to gravity. As you go up, you will feel yourself lighter and lighter. Understood? The people who summit any mountain top, like for example any mountain which is height which has much more height than 5,000 meter, will feel much more lighter over there, because the acceleration due to gravity, that is the gravitational pull of earth, which is comparatively less over here. Next is variation of g due to depth. It's very much important when we consider this. Variation of g with respect to depth. We already told you, as the height increases, the g will also decrease. The small g I'm talking about. Now, as you go inside, what will happen? At surface it is maximum. Surface it is actually 9.8 meter per second square. So what is when you go inside the earth? When you go inside the earth, as per the equation, there will be a minus over here, that is r minus h. That is, the r will be the total radius of the earth. When you go inside, the radius will decrease. Okay, so as the radius will decrease, the mass is also considerable, because earth, as the radius increase, that much mass we just neglect. That is, the volume will be decreased. Radius decreased, volume will be decreased. And the volume will be decreased, mass will be decreased. If mass will be decreased, hence acceleration due to gravity will also decrease. As a result, there won't be a force much more applied over here. Okay, we can read the sentence over here, which means the value of m to be used in equation number 5, that this is the equation number 5 which is specified on your textbook, also decreases. As a combined result of this change, r and m, the value of g decreases as we go deep inside the earth. This will be much more elaborately explained when you go in your higher secondary standards, 11th and 12th. Much more it will be explained. As of now, for your syllabus, this is more than enough for you people. I hope you people understood. Going for the next part, mass and weight. Everybody know about this. We have already learned about mass and weight with respect to all this concept in your 9th standard. Mass is actually amount of matter present in the object or any body. Mass is amount of matter present in the object. The SI unit of mass is also kg. Weight. Now weight is very much important with respect to this chapter, because what is the weight of a person? The weight of a object is defined as a force. It is a force. Do not get confused with mass and weight. They are absolutely different with respect to scientific terms. They are absolutely different from each other. Weight is a force, but mass is the amount of matter present. Mass will be an amount and weight will be a force with which the earth pulls or attracts the object with a certain force. So, as you know, force is equal to mass into acceleration by Newton's law. Force is equal to mass into acceleration. Here, with respect to gravitation, the acceleration will be just nothing but acceleration due to gravity, that is the small g, F equal to mg. G will be again capital G with respect to our previous equation which I have shown, page number 8, fifth equation, same, the legendary equation. You will be able to understand this part. The weight of an object will be the force applied onto that object by Earth or any other planet. Understood? So your mass will remain same. Wherever you go, your mass will remain same, but your weight may not remain same. Like for example, when you are on the surface of the earth, you may weigh 60 kg, or when you just go outside the earth's orbit, I mean when you go to the space, at that time you won't feel yourself you have weight, because of the acceleration due to gravity is missing over there. That is, the force will be equal to m. The g will be missing. So force will be equal to m. That means mass remains. That is, the total mass will be 60 kg only, but weight will be 0 when you go to the space. That is, weight will be equal to 0. This will be 0. Weight will be equal to 0 when you are in space. Just listen carefully. When you're space, weight will be equal to 0, but mass will remain 60 kg only. And one more thing you have to understand with respect to the one small point. If weight is equal to k, we measure in weight, even in normal terms, in our local normal terms, in like a layman term, we measure weight with respect to kg only. But why we can't measure with respect to Newton? Since a unit of force, if it is a force, weight is weight, if it is a force, why cannot measure it in newtons? Because due to the practical difficulty, so we cannot measure any weight with, like, if you go to any store, you cannot take one 753 Newton of sugar. It is very much no, it's not practically possible to understand that. Normally we just say kg. So you'll read this part. For us, the both mass and weight and measure of the weight kilograms, which are unit of mass. Scientific language, we can say that if a person having 75 kg, we are talking about the mass of the person. That means weight of the person will be 75 point. So weight of the person will be, according to the equation which is given over here, 75 into 9.8 is 735 Newton. Okay, so weight of 1 kg mass is equal to 9.8. So our weighing machine tell us the mass. The two, like, in this way, the scale balances the mass and the weight together. Ultimately, this is the main reason for we are using mass and weight as same for normal practical purposes. But scientific terms, both are actually different from each other. The next part we are talking about is about a free fall. So whenever a body fall, when the body will just fall under the influence of gravity, then we can call it as a free fall. So no push will be there. The body should fall from a particular height. Just imagine we are throwing a ball up and just coming down only with the influence of gravity. That is known as free fall. The rate at which the free fall happening is 9.8 meter per second square. This 9.8 meter per second square means after every second the speed will be increased by 9.8 meter per second. That is impact. That's why whenever we just throw an object from a particular height, the impact will be much more with respect to the acceleration due to gravity. Like for example, if you drop a small glass ball or a small glass sphere from a particular height, like imagine a 2-inch, it won't break. Just increase it into a 1 feet, there's a chance to break, but not sure. At 10 feet, it will definitely break, because as the height increases, the gravitational pull of Earth will also increase. That's why this gravitational fall, that is a free fall. What do you mean by this free fall? That is the 9.8 meter per second square. You will be able to understand this part when you just read the 11th page of your chapter. That is the 11th page of your textbook. Free fall, there is a entire para on that. You will be able to understand that. Just go. Definitely you have to read that part. Next we are talking about escape velocity over here. What is an escape velocity? Remember last lecture I told you, when you pull a string and you tied a knot and you tied a stone at the end and you just make it into a circular motion, you will feel a pull of the stone. You definitely understand when you leave the string, it will just go away from the your entire force of attraction. Just go. It will just you'll be able to just throw that stone. In the same way, here also there is an interesting factor with respect to escape velocity. When you talk about escape velocity, just look at carefully. This is a satellite which should be revolving around Earth at a particular velocity. Remember students, at a particular velocity is must. Beyond that velocity, it will escape the gravitational pull of the Earth and will go into space. If it is having less than that velocity, that a particular velocity, it will definitely come under the influence of the gravity and just fall on the surface of the Earth. Very carefully, this dotted line tells you how it will fall onto the earth if there is no particular velocity. There should be a particular velocity given with respect to that satellite so that it can revolve around the earth for a longer period of time. Normally all the satellites which is revolving around our earth have a particular velocity, a particular satellite orbital velocity. Beyond that it will go into the escape velocity category, or below that it will just come and fall into earth. So there's a particular orbital velocity should be provided to that satellite so that it can revolve around the earth properly. So here we have to understand how it works on. Here, due to the rotation of the earth as well as the revolution of the satellite, we'll be able to understand there is a centrifugal force which is pushing the satellite outside, and there is a centripetal force which is pulling it towards the surface. So in between that push and pull, the satellite is balanced. Thus we get a particular orbital velocity and the satellite remain in the orbit for a longer period of time. Next part is about a theoretical part of the same thing, how it works on. We carefully just go through this part. An object going vertically upward from the surface of the earth having an initial velocity equal to escape velocity. Okay, escapes the gravitational force of the earth. Where it will go? Definitely it will go beyond the gravitational force of the earth and it will end in space. The force of gravity being inversely proportional to square of distance. Remember the fifth equation I told you? The force of gravity will be inversely proportional to the distance, that is gm by r square. Becomes zero only at a infinite distance of the earth. When this is zero, if it is remaining very much infinite, when the denominator will be infinite, at that time you will be able to understand the entire force will be equal to zero. This means that the object to be free from gravity of earth, it has to reach infinite distance from the earth. The object will come to rest at infinite distance and it will stay there at infinite distance. It will go beyond the gravitational pull and it will remain there only. So there will be actually no force of attraction in between them. So here the kinetic energy is given by half mv square, as you know, half mv square. Here the v we can consider as escape velocity over here. Here v to the base escape, we can consider the escape velocity. The potential energy can be given by minus gm m by r. Why it is minus? Because there is a potential energy which is going, just we are taking that satellite and we are going up. So because of that, since the direction is there, the potential energy remains minus. So the total energy remains kinetic energy plus potential energy. You will be able to find out this is the total energy. Ultimately, since the kinetic energy will be zero, like for example on the surface of the earth, kinetic energy will be half mv square and the potential energy will be half gm by r. Total energy will be kinetic energy plus potential energy. Ultimately, we will get this part. And next is, if it is in infinite distance, kinetic energy remains zero and potential energy remain again this, but with respect to the r it will go on. So entirely at infinite distance the total energy remains zero. At on the surface of the earth the energy will remain like this. So that with respect to this chapter, I'll give you assignments with respect to this chapter. I hope you will understand and complete the assignment properly, and I request you to just go through the textbook once again with this lecture